Hello students, today I am here to give a third session on packaging and circuit boards, interconnection and signal integrity. Today let me see what are the topics to be covered in this package and circuit boards, interconnection and signal integrity. Right? Again, we go for referring the same textbook, an embedded systems approach using Verilog by Peter J. And it is given in the chapter 6 in this textbook. Let me see the different topics which has to be covered. IC packages, PCBs, signal integrity, differential signaling. Before studying these IC packages, PCBs, signal integrity, differential signaling, let us refresh the things which I have covered. Just let us see how we go for IC fabrication or IC manufacturing. Let us see the different manufacturing steps involved in IC fabrication. We go for lithography, etching, deposition, chemical mechanical polishing, oxidation, ion implementation, and diffusion. Let us see what is lithography. You know what is lithography in the previous topics. Let me refresh the things what I already studied. It is a process to define a pattern wherein a photoresist material is uniformly applied on the wafer surface and then baked to harden. Later, UV light is projected through mask information and it is selectively removed. Right? Etching. The unwanted materials are removed from the surface of the wafer. This we go for calling it as etching here. Deposition. By the method of physical wafer deposition and chemical wafer deposition, materials are applied on the wafer. Chemical mechanical polishing. A polarization technique by applying a chemical slurry with etchant agents to the wafer surface. Oxidation. In the oxidation process, oxygen, that is dry oxidation, or HO, that is wet oxidation molecules, convert silicon layers on top of the wafer to silicon dioxide. Right? Ion implementation, the most widely used technique to introduce dopant impurities into the semiconductor. The ionized particles are accelerated through an electrical field and targeted at the semiconductor wafer, which we go for calling it as ion implementation. Diffusion. A diffusion step following ion implementation is used to anneal bombardment-induced lattice defects. These are the steps involved in manufacturing of IC. And just in brief, I have given what is lithography, etching, deposition, chemical, mechanical, polishing, oxidation, ion implementation, and diffusion. Let me go for the IC packages. During the production of semiconductor device, IC packages is the last step in the process. During this stage, the semiconductor blocks gets covered in a package. That is, if the semiconductor blocks gets covered in a package, for what purpose we are going to go for cover in a package? To protect the IC from corrosion or physical damage, protect the IC from moisture, protects the IC from airborne contaminants. It removes heat and allow mounting of electrical contact connecting to the PCB. Right? For this, just you go for having the semiconductor blocks will be covered in a package. To have this advantage, just we go for covering the semiconductor in a package. Integrated circuit packaging refers literally to the material that contains a semiconductor. Right? Let me see the different types of IC packages. If you there are many types of IC packages with different physical, electrical, and thermal properties. Let me come to know the different types of IC packages. The lead frame type, substrate type, or flip chip technology, wafer level packaging. These two, the lead frame type, substrate type, or flip chip technology, is in your syllabus, and this is an extra information which I am giving here. Wafer level packaging. Let me see one by one. The lead frame type. Lead frame type packages. In case of lead frame package, the IC is fixed to the bottom of the cavity. Right? In case of lead frame package, the IC is fixed to the bottom of the cavity. Find gold wires are connected from bonding pads on the edge of the IC. Say, just you can see the gold wires are connected from bonding pads on the edge of the IC. In turn, these gold wires points on the lead frame as shown in figure A. They are connected in to the lead frame in turn. The cavity is then lead frame which is a metal again. A lead frame which is a metal work leading to the external package pins. The cavity is then scaled to protect the IC and the wires. This is about your lead frame type, the first type of the package. Let me go for the next one. Substrate type or flip 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 chip technology package. Recent packages for these ICs have adopted flip chip technology. The connection pads on the IC are covered in conduction material forming bumps. You can see this. These are the bumps. The IC is then flipped over and affixed to the substrate of the package with the bumps in direct contact with the substrate connection points. The connection points lead to the pins of the package. This is how your substrate type or flip chip technology package. Finally, we come for wafer level packaging. In a wafer level packaging, the construction occurs on the wafer face, creating a package the size of a CPU. This is about your substrate type and wafer level packaging. Right? Looking for the next one. Let me see what is PCB. The interconnection between different ICs on a common substrate is called a printed circuit boards or printed wired boards. Right? You can go for calling as PCB or PWB. Usually we go for calling it as a PCB. This consists of layers of fiberglass, right? Or we can go for using any other insulating materials, separating layers of conducting wires, usually made up of copper. The metal is deposited in a layer on a glass fiber sheet and then etched using a photolithographic process similar to that we used in manufacturing ICs. Right? Several layers are sandwiched together. Small holes are drilled through the layers and coated with metal to form connections called via between the layers. The completed PCB contains all the circuit wiring needed for the product. This is the information about your PCBs. Let me go for saying the different types of PCBs and the packages involved in this one. If we want to see the different types of PCBs here, we can see through hole PCBs, where in which they go for use insertion type packages. In this through hole PCBs, they go for using insertion type packages. In this, you go for having dual in packages, right? Pin grid array. The other type of PCB is surface mount PCB. In this, they go for using surface mounting type packages. It may be quad flat pack, ball grid array. We go for let me go with one by one. Through hole PCBs. In this through hole PCBs, this refers to the process that through hole components, as the name itself tells you, through hole components are soldered onto the baseboard by wave soldering or hand soldering with components lead going through drilled holes the of PCB. That is through hole. Just they go for having lead going through drill holes of PCB. A metal alloy with a low melting point is melted into the holes to form electrical connections between the pin and the PCB wiring. To have an electrical connections, right? What you are going to do it? Alloy with a low melting point is melted into the holes, right? It may be in between the connection between the pin and the PCB wiring. Products using this form of manufacturing needs ICs in insertion type packages. It may be dual in line packages and pin grid packages, right? We go for insertion type packages. In this insertion type packages, we go with the dual line packages. Dual in-line packages have two rows of pins with zero point 0.1 inch spacing. See here, two rows. It is this one row, and the opposite side you can see another row. They have zero point 0.1 inch spacing in. These were among the first IC packages to be introduced, being used for small-scale integration and medium-scale integration components. They were limited in the number of pins they can provide with a 48-pin dual in-line package being about the largest practical size, right? The maximum number of pins which you can go for having in case of a dual in packages is 48 pin. Let me go for a pin grid array. ICs requiring more pins can be packed in a pin grid array, right? Package having up to 400 or more pins, right? They are mainly used for ICs such as computer CPUs that are mounted in sockets so that they can be removed here. They will be mounted in a socket. This can be removed here, right? Let me go for the second type of PCB. Surface mount PCB or surface mount technology. We go for calling it as SMT. Surface mount packaging follows the technology of mounting or placing the components directly on the printed circuit board surface. As you can see here. This has the advantage of reduced manufacturing cost, right? Finer feature size and increased circuit density. An electrical component mounted in this manner is referred to as surface mount device, right? SMD. Surface mounting type packages have pins or connection points that come into contact with a metal pad on the PCB. Solder paste is applied between each pin and pad and melted, forming the connection. Let me see. In case of your surface mount PCB, just we go for using surface mount packages, right? In that we go for having quad plat package, we referred as a QFP, and ball grid array BGA. In this, let me go for a surface mounting packages. Quad plat package or QFP, it is shown here in this figure. A quad plat package is a surface mounted integrated circuit package with gullwing, right? Leads extending from each of the four sides with up to 200 pins here. As you can see here, this gullwing here. The spacing between pin varies from 1 mm for the package with fewer pins down to 0.65 mm for the higher pin count packages. The gap between the each pin may be 1 mm, or it may be if the pin number increases, it may go up to 0.65 mm. Fine pitch QFP packages allow increased pin count up to nearly 400 pins by reducing the pin spacing to 0.44 mm. Right? One can go with 1 mm, right? If the pin count is less, still we go with 0.65 if it is somewhat greater than that one. If it is still, if you want to go for 400 pins, just we go for reducing the pin spacing to 0.4 mm. The package are suitable for manual handling and assembly. This is about your QFP, right? Let me go for ball grid array RPGA. The package in use for high pin count ICs is the ball grid array package, right? Depending on the package size and pin spacing, BGA can accommodate ICs with up to 1800 pins. This is advantage over your QFP. Higher pin count BGA packages are also being developed, right? This shows your BGA. This is about your quad pad package, ball grid array. Let me see the comparison between your surface mounting and through hole mounting of different types of PCBs here. If you compare with the size, surface mount packages are smaller in comparison to through hole packages, component density. If you compare the number of transistors or components used here, component density. Surface mounting packages have a comparatively high component density as well as the density of connections. Assembling. Tiny errors are automatically corrected by the molten solders that pull components close together due to tension in surface mounting packages, unlike through-hole packages that cannot afford even the slightest of errors while making holes. This is because the alignment once made cannot be corrected. Right? This is the different comparison between your surface mounting and through-hole mounting with respect to assembling. Electromagnetic compatibility. Electromagnetic compatibility. It is the ability of different electronic devices and components to work correctly even in the presence of other devices that emit electromagnetic waves. Surface mounting packages have a better EMC performance. Right? With respect to cost, the cost of production is also lower than that of the through-hole packages because of automated method. In case of surface mounting, it will be cost will be also less. There's an extra additional things which I have given you. Right? Let me go for multi-chip modules. Right? In recent times, high-density packages techniques have been developed for use in products where spacing is constrained. Right? Multi-chip modules attach the base chip to a ceramic substrate. See figure here. Right? Interconnection wires and passive components. The passive components means it may be consisting of resistors and capacitors are also printed or soldered on the substrate. You can see some area just they soldered the resistors, right? Even the capacitors, everything on the everything here itself. The compute module is then encapsulated with external connections made through package pins to a PCB. The the complete module is encapsulated with the external connection, right? External connections made through package pins to a PCB, right? Even denser packaging can be achieved by building in three dimensions rather than laying them out on a two-dimensional surface, right? Just this about explanation. For example, chip stacking involves placing two or more chips in a vertical stack. Connections can be made between adjacent chips by metal contacts and between chips and the containing packages by band wires. Several flash memory manufacturers are using these techniques to provide high capacity storage in very small packages. As demand for high performance mobile devices increases, we can expect to see continued development of this high density package technology or techniques here, right? This several, just as I told you, it will be attach the base chips to the ceramic carriers, right? This can include the thin film passes. As I told you, it may be consisting of passive components, right? Passive components means resistors and capacitors, as I told you, right? And discrete components, external connections for PCB mounting. Just we can go for connecting that to the PCB mounting. And example is your cell phones. It is ideal for high density applications. This is the points which has to be remembered here with multi-chip modules. Signal integrity. Signal a signal change must propagate from the source drivers through the bond wires, right? Through the bond wires, package pins, right? Even with the PCB traces, right? It has to propagate here. Along this path, there are several influences that can cause distortion of the signal, introduce noise. When this signal propagates over bond wires, package pins, PCB traces, various effects will cause distortion and noise. Right? The term signal integrity the term signal integrity refers to the degree to which these effects are minimized. Signal integrity means refers to the degree to which these effects are minimized. A change in a signal value causes in the current flowing through the PCB trace. This causes a change in the electric and magnetic field around the trace. Propagation delay of these fields determines the speed of propagation of signal change along the trace. In PCB materials, the maximum propagation speed is approximately half the speed of the light in a vacuum. Half the speed of the light in a vacuum. Thus, the speed of the light is 3 into 10 to the power of meter per second. We get 150 mm per nanosecond as a speed for signal propagation along a PCB trace. Right? For low speed designers and small PCBs, this element of total path delay is insignificant. However, for high speed designs, particularly for signals on critical timing path, it is significant. Two cases in point are the routing of clock signals and parallel bus signals. Right? If a clock signal is routed through paths of different lengths to different ICs, we may introduce clock skew. Similarly, if different signals within a parallel bus are routed along paths of different lengths, changes in elements of the bus may not arrive concurrently and may be incorrectly sampled the destination receiver. See here. If different signals within a parallel bus are routed along paths of different lengths, right? If you have a different path length, changes in elements of the bus may not arrive concurrently. At a time, we can't receive it and may be incorrectly sampled the destination receivers, right? In these cases, it may be necessary to tune the timing of the system by adding to the length of some PCB traces to match propagation delays. For this, just we go for using CAD tools used for PCB layout offers features to help designers perform such tuning semi-automatically. This is about your signal integrity, right? This let me go for ground bones. A major signal integrity issue in PCB design is ground bones, which arises when one or more output drivers switch logic levels. Right? When one or more when one or more output drivers switch logic levels. During switching, both of the transistors in the driver's output stage are monetarily on and transient current flows from power supply to ground. Power supply to ground. Ideally, the power supply can source the transient current without distortion. In reality, however, there is an inductance in both the power as well as the ground connection as in shown in figure. This is shown here. Right? The inductance causes voltage spikes in the power supply and ground on the IC. Right? This inductance cause the voltage spikes in the power supply and ground on the IC. This can cause voltage spikes on the other output drivers, right? This this means voltage spikes, right? On the other, it may this can cause voltage spikes on other output drivers, causing false transition in the receiver at which they are connected. It can also cause transient shifting of the threshold voltage of receivers on the IC, causing false transition at those receivers. The main thing is just you have to consider the spikes caused due to the supply and the ground in between. This voltage spikes on the other hand, it may with respect to the other drivers, right? They may cause false transition in the receivers to which they are connected, right? For this, in this, it may also cause transient shifting of the threshold voltage. The threshold voltage may also shift here, right? And threshold voltage, when it shifts, threshold voltage of receivers on the ICs, causing, if the threshold voltage shift means false transition at those receivers may occur here. This is about your ground bounds. How to minimize this bounds? Right? In order to reduce this effect of ground bounds, a number of important measures can be taken. First, we can place bypass capacitors between power and the ground, right, around a PCB. These capacitors holds a reserve of change that can quickly supply the needs of switching drivers. A common rule of thumb is to place a capacitor close to each IC package. Value may be 0.01 microfarad to zero point 0.1 microfarad are used commonly. Right? Second, we use separate PCB layers for the ground and power supply. This is shown in figure A. This gives a low inductance for the power supply current and its ground return. It also has other benefits mentioned below. Right? Third, we can limit the rate of voltage change, that is the slew rate, and limit the drive current of the output drivers. These actions limit the rate of change of current and so limit the inductive effect of the change component, such as modern FPGAs have programmable output drivers that allow selection of slew rate and drive current limits. Reducing the slew rate means that a signal takes longer to change from one logic level to the other as illustrated in figure B. See here, this slew rate is limited here. This is the I slew rate which you can see here. Hence, limiting slew rate may increase propagative delay through circuits, consequently requiring a reduction in clock rate. This is a case where trade-off between speed of operation and noise immunity may be required. Finally, we can use differential signaling to make the system more immune to noise induced by ground bounds. Right? This is about your how you go for minimizing the bounds here. Just you go for using bypass capacitors, right? Separate PCB plans, and just you go for having slew rate limited here, right? Next we go for transmission line effects. Another signal integrity issue for high slew rate signals is noise due to the transmission line effects, right? When the time for a transition between logic levels is similar to or shorter than the propagation delay along a signal path, the transition is affected by reflection at the driving and receiving ends of the path, and the signal may suffer from practical transition, right? Overshoot, undershoot, and ringing. See, overshoot, ringing, and undershoot. The main design techniques for managing transmission line effects involve appropriate layout and proper termination of PCB traces. By running a trace of specific dimensions at a controlled distance between the ground and the power planes in the PCB, we create a strip-line transmission line with a controlled characteristics impedance where the transmission line effects are less critical. We can run a trace over just one plane, creating a microchip transmission line. Right? You can refer this with the given text material, whatever material which I have given. Right? For more information. We go for electromagnetic interference. Transitions between logic levels on a signal cause the electromagnetic fields to propagate around the PCB trace. Right? Here, transitions cause electromagnetic fields here. Some of the field energy is radiated out from the system and may impinge on the electric systems when it induces noise. Right? Some of the field energy, right, is radiated out from the systems and may impinges on the other electronic systems where it induces noise. This forms of unwanted coupling is called electromagnetic interference. Right? Let me come for crosstalk here. Electromagnetic fields from an aggregator PCB trace can also impinge on adjacent traces, inducing crosstalk on the victim traces. The closer the traces and the longer their parallel paths, the more pronounced the crosstalk effect. Right? As with other signal integrity issues, appropriate PCB design techniques such as routing traces close to ground on power plants can reduce EMI and crosstalk by containing the electromagnetic fields. Limiting slew rates of transitions also reduces the radiated energy and so reduces EMI and crosstalk. Let's go for the last previous differential signaling. Differential signaling is the method of electrically transmitting information using two complementary signals. Right? Just differential signaling is a method of for electrically transmitting information using two complementary signals. The technique sends the same electrical signals as a differential pair of signals, each in, in its own conductor. The pair of conductors can be wires typically twisted together or traces on a circuit board. The receiving circuit responds to the electrical difference between the two signals rather than the difference between a signal wire and ground. Right? SP minus SN. Right? The opposite technique is called signal-ended signaling. The opposite technique is called single-ended signaling. The opposite technique is called single-ended signaling here. Differential pairs are usually found on PCB in twisted pairs and ribbon cable and in connectors. The use of differential signaling is based on reducing systems susceptibility to interference. Right? Here, rather than transmitting a bit of information as a single S, we transmit both the positive signal and negative signal SP and SN. At the receiving end, we sense the voltage difference between the two signals SP S and SP minus SN. Right? If SP minus of Sn is a positive voltage, then S is received as a value 1. SP minus S1 is 1 means then S is received as a value 1. If SP minus Sn is a negative voltage, then S is received as 0. This arrangement is illustrated in figure below here. The assumption behind the differential signal approach is that noise is induced equally on the wires for both SP and Sn. Such common mode is cancelled out when we sense the voltage difference. To show this, suppose a noise voltage Vn is induced equally on two wires. At the received, we sense that voltage, right? Sp plus of Vn minus of Sn plus Vn, right? If we take out the bracket here, Sp plus of Vn minus of Sn minus of Vn, this plus Vn and plus V noise and minus V noise get cancelled. We go for getting as Sp minus Sn. For the assumption of common mode noise induction to hold, differential signals must be routed along parallel paths on a PCB. While this might suggest a problem with crosstalk between the two traces of The fact that the signals are inverse of each other means that they both change at the same time and crosstalk effects cancel out. As well as rejecting common mode noise, differential signaling also has the advantage that reduced voltage swings are needed for a given noise margin. Even though each of SP and SN switches between the low voltage and high voltage, that is VOL and VOH, the differential swing at the receivers in between VOL minus VOH and VOH minus VOL, that is twice the swing of each individual signal. Reducing the voltage swing has multiple follow-on effects including reduced switching current, reduced ground bonds, reduced EMI, and reduced crosstalk with other signals. Thus, use of differential signals can be very beneficial in high-speed designers. Right? For that, just you go for using the differential signaling. For more information, just refer your text material which I have given. Finally, we go for summary. We came across IC packages. We studied lead frame type, substrate type, wafer level packaging. When you come to know the different types of PCBs, and that PCBs involved many type of IC packages. Through hole PCBs used insertion type packages. We studied about dual in packages, pin grid array. When you came surface mount PCB, we studied about the surface mounting type packages used in surface mount PCB. It is QAFP, quad plate pack, ball grid array, and we studied about multi-chip modules, signal integrity. Finally we studied about differential signaling. Right. After you finish today's presentation, please take 2 minutes to leave a comment about your experience with this presentation. I can see that our time is just about up to finish. In the next session, I'll be talking about the module 5, that is design methodology. Thank you for being here today. Thank you.